Hello everyone. Before we get started, is my audio okay? Can everyone hear me? All right, cool, awesome. All right, let's get started with today's tutorial. So this week's tutorial, we are essentially starting the last topic, which is on uh, complexity theory or intractability. So the whole point of the last topic is to kind of give you a kind of introduction to the kind of problems or to the kinds of questions that we often ask when we are trying to solve problems or trying to show that a problem can't be solved efficiently. So, whenever you come up with a problem or you are introduced to a problem for the first time, you might not know how to solve it, and in fact, one of the things you might want to do is to show that you can't solve this in polynomial time. So often when you come across a problem in the wild, you want to ask the following questions. Is this maybe not this color? Um, so I'll do. Okay, I'll just do that. So you often want to ask the following the problem. Is the problem easy to solve? And what we mean by easy is, can you come up with a polynomial time algorithm for this? So by easy, we mean polytime algorithm. So maybe the simplest algorithm would be a brute force kind of algorithm. So if you just look at any uh, any brute force algorithm, what is the running time of the brute force algorithm, and then you might want to then speed up the algorithm itself. So if the problem has a polynomial time algorithm, we typically say that the problem is easy. But what you'll see is a lot of the common problems you'll come across in the real world are actually hard in general. So lots of problems are hard in general. And what we would like to do is to kind of figure out exactly why the problem is hard. So in complexity theory, what we want to do is to kind of get to the root of the difficulty of the problem. So rather than just saying, oh, this problem is hard, we want to figure out exactly why this problem is hard. Uh, and so this, and so to understand where the hardness of the problem comes from, we introduce this notion of a reduction. So a reduction is essentially a way to relate two different problems together. So even though two problems might look very different, maybe one comes from a geometry setting, and then one comes from a combinatorial setting. Like even though the two problems are formulated very differently, in fact, what you'll see is a lot of the times there is some connection between them. And what we would like to do is to kind of connect the dots between a class of problems and show that, in fact, all of these problems are equally as difficult as one another. So instead of just saying, "Oh, this problem's too hard," and things like that, what we would like to do is to come up with some kind of theory or some kind of hierarchy of uh, problems, so that we can kind of build a repertoire of different techniques to solve different kinds of problems. And so the usefulness of a reduction is it illustrates the actual relationships between these different problems. So um, what you'll see later on as we do the problems is that even though there are different problems in different settings, actually a lot of them are very similar to each other. Okay, So once we talk about reductions and everything, then we come across a lot of complexity classes. So now we can start to build a theory or a hierarchy of complexity classes, so that now we can talk about uh, the common relationships or the common properties that these problems have with each other. So the first complexity class that you'll come across is P. So in other words, the class P is a set of all problems for which we can solve in polynomial time. So these are solvable in poly time, right? So all you need to do is give me a polynomial time algorithm for this problem and show that this is correct, and then the problem would be in class P. Here you need to be a little bit careful because it's not exactly obvious what poly time means. So polynomial time here just means polynomial in the size of the input. Right. So if you have an input, for example, an array of n integers, then we would like the algorithm to be to run in some polynomial in the size of the array. If your input is a graph, for example, so if you have a graph input, then we say that it's polynomial time in terms of its vertices and its edges. So to represent a graph, you would need to process the vertices and the edges. So it takes all of n plus n to encode your graph, and so it has to be polynomial in m and n as well. Okay, so these are the problems solvable in polynomial time. Then you have NP. Now NP aren't necessarily the problems that are solvable in polynomial time, but these are problems where you can verify solutions in polynomial time instead. So these are verifiable in polynomial time. And what I mean by verifiable is if I were to give you, um, if I claim that this is a solution to your problem, then it should be very easy to check that this solution is actually a correct solution. So, for example, if I have a Sudoku, let's say, okay, we'll do a 2x2 Sudoku, and then I say, okay, this Sudoku has a solution, and then I give you, oh, maybe not this, and then I give you the solution. So maybe this is 1, 2, 3, 4. Then you can check very easily that this is a solution because, well, every row has distinct integers, every column also has distinct integers, so on and so forth. So these are problems where we don't necessarily know how to solve them in polynomial time, but if you were to give me a solution, I can check very easily that this is a solution. So note that this is only true for solutions. So it doesn't check non-solutions. So if you don't have any solutions to a problem, then the NP-ness doesn't really tell me anything. It's only that if I give you a solution and this is actually a correct solution, then it is easy to check that this is a solution. But if I give you an incorrect solution, I can verify very easily that this is not a solution, but it doesn't mean that a solution doesn't exist uh in the problem. It just means that I won't be able to find the a solution. Because if I were able to find a solution, then I would be able to solve it in polynomial. So this basically just says, well, if you give me a solution, I can check that it is a solution, or I guess I can check that it is not a solution, but I won't be able to, like, if it is not a solution, then I won't be able to find a solution in polynomial time. or at least we don't know the way of finding the actual solution in polynomial time. Cool. And so in both P and NP, we often deal with decision problems. So decision problems are just problems for which the output is either yes or no, or true or false. And so if I give you a solution, and this is actually a solution to my decision problem, then of course I can check that the decision problem is actually a yes instance. So when it comes to NP, it's a little bit more than just, oh, I can't solve it in polynomial time. It's just that I can verify, I can check that the solution is correct in polynomial time. Okay, so then we come to NP hardness. So oftentimes when we develop complexity theory and complexity classes, we often have two types of classes. So we have the base class, which is my NP class. But then on top of my NP class, I have these two other kinds of classes, one of which is called NP hardness, and one of them is called NP complete. NP hardness just tells me that these are the problems for which, if I know how to solve it, then I can solve every problem in NP. So if I can solve, then every problem can be solved in NP. In other words, if I knew of an algorithm that solved any problem in NP hard, then in fact I can use this algorithm to then solve every problem that also lies in the class NP. And so therefore what you can think about is, well, NP hardness really tells you that these are the problems that are much harder than problems in NP, right? Because if a problem in NP hard was easy, then in fact every problem in NP was also easy, because generating an algorithm for any problem in this class will give you an algorithm for every problem in this class. And so this is useful because now if I just look at any problem that belongs in NP hard, then in fact that will tell me a lot about problems in NP. But of course, NP hardness problems are not necessarily problems that are in NP. In fact, you could get much harder problems that lie in NP hardness. NP hard just tells you that these are problems that are harder than problems in NP, but it doesn't tell you that, in fact, these are the problems that make NP easy. So then we have the final class, which is NP complete. And NP complete are just problems that are harder than NP, but also belong in NP. So this is NP and NP hard. And so NP hard just tells you that these NP complete problems are among the hardest of NP problems. And the fact that it belongs in NP means, well, it is actually the hardest types of problems that are also one in polynomial. Does all of this make sense to everyone? Are there any questions with any of these complexity classes? We will talk a bit more about them as we go through the tutorial, but this is to kind of give you a brief synopsis of kind of the end goal of the last topic. So it's not really about intractable problems per se, but it's really about connecting different problems together. And in fact, the notion of a reduction is something you would have seen already, where you take a problem, you take an instance of the problem you want to solve, and then you just basically transform it into another instance of a problem that you already know how to solve, or you take an instance of a problem that's already hard, and then you transform it into an instance of your problem, and then you show that your problem is hard. So, let's get started with the tutorial. So here we're going to look at two problems, and these problems might seem very different, but in fact we'll show that that they're actually equivalent problems. So let G be a graph. Here, whenever we say a graph, we always mean simple and undirected and unweighted. So every time we just say graph, we just mean undirected and unweighted. If there is a weight, then we'll specify that it's weighted, or if it's directed, then we'll specify that it's directed. So we say that a subset of vertices is an independent set. So it's an independent set if essentially no pair of vertices in my subset are adjacent. So in other words, it's an independent set if there's no edge connecting the vertices. So maybe you have a graph that looks like this. Then these vertices here form my independent set because no pair of vertices that are highlighted share an edge. But of course, the moment I add in this vertex, it no longer becomes an independent set, right? Because you can see that these two pair of vertices share an edge, these two vertices share an edge, and these two vertices share an edge. So if I add in the blue vertex, then it's no longer independent. But if I just look at the yellow vertices, then they form an independent set. Okay. Okay. And then we say that a subset of vertices is a vertex cover. So it's a vertex cover if essentially every edge has an endpoint that has some endpoint that's in S. So you don't need both of your endpoints to be in S, but you need at least one of your endpoints to be in S. And then we say that this is a vertex cover. So for example, the blue vertex itself is already an independent set. Sorry, is already a vertex cover, because if you look at every edge that belongs in my graph, then you can see that all of these edges have an endpoint that's in S, which is my blue vertex. Cool. So these two concepts are very important, but they seem very distinct. They seem very different. In fact, what we'll show is that actually computing independent sets and vertex covers are actually equivalent. So let's have a look at these two decision problems. So my input is a graph and an integer, and the independent set problem is to decide if G has an independent set of at least K, and then the vertex cover problem is given a graph and an integer, you want to decide if a vertex cover if G has a vertex cover with at most K vertices. Okay, so you can see that the interesting problem here is we want to maximize the size of my independent set, and we want to minimize the size of my vertex cover. Right? The minimum independent set is trivial because the empty set itself is already an independent set, and the maximum vertex cover problem is trivial because you just take every vertex, and that is a vertex cover, and that is the maximum vertex cover. So in fact, we'll look at the maximum independent set, which is to say the maximum number of vertices that is also an independent set. And for vertex cover, we want to find a vertex cover that minimizes the number of vertices. Okay. So for part A, you're given a graph and you're given a set of vertices which form an independent set. You want to show that the vertices that are not included in my independent set is actually a vertex cover. So you can see, for example, right, these three vertices here form an independent set. And then if I look at the set of vertices that are not in my that are not in the vertex in the independent set, then this is actually a vertex cover because every edge is covered. But why is this true in general? So you can't show that this is true for just one graph. You want to show that this is true on every graph. So why do we think that the complement of an independent set is actually a vertex cover? Are there any thoughts? So maybe I'll bring this up again. So if I have an independent set, then I claim that the vertices that are not in my independent set form a vertex cover. But why is that true? So let's start with uh, so let I be an independent set. And then I'm just going to define S to be the V minus I just for ease of notation. So why is S here a vertex cover? So if I look at any particular edge, so um, consider some edge UV. What I want to show is at least one of U and V has to belong in S. So the claim that I want to show is at least one of U and V belong in S. But why is this true? Right? So, okay, so what happens if neither of them are in my set? So, um, if U and V are not in S, then what you get is, well, they have to belong in I, right? Because S is just a set of vertices that are not in my I. So in fact, what you get is both of these vertices have to belong in the independent set. But why is this a contradiction? So now I have an edge. So I have two vertices, and I know that these two vertices are share an edge. And what I said is, well, if both of them are not in S, then well, in fact, both of them must be in my independent set. But if you look at the definition of the independent set, these are vertices that don't share any edges. So if you take any pair of vertices in my independent set, they don't share an edge. So in fact, this is a contradiction then. Uh, but this is a contradiction. Okay. Oops. Contradiction. Since I is an independent set. Right, because um, U and V share an edge by our assumption. So in fact, if U and V don't belong in my vertex cover, so if there's an edge that isn't covered, then the two endpoints of my edge. So if I look at a picture, so suppose I have a graph and I consider just an arbitrary edge. Well, if it's the case that both of these endpoints are not in S, so this vertex here and this vertex here both belong in I, then this is a contradiction because that means my independent set itself has a pair of vertices that share an edge, but then this is not an independent set. So in fact, that means that at least one of the endpoints in every edge must belong in S, and so therefore S has to be a vertex cover. So therefore, at least one endpoint uh, belongs in S, and this is true for every edge, right? Because this argument holds for any arbitrary edge. So in fact, it holds for every edge. And this, by definition, just tells me that S is a vertex cover. Does this make sense? Are there any questions with this argument? If there are no questions, then we can quickly prove that the other direction. Yep. So the edge needs to be covered. Yep. So this is true for every edge. So every edge needs to be covered. So in fact, my set itself is a vertex cover. Okay. So we can quickly prove the second direction. So now I'm given a vertex cover, and I want to show that the complement of my vertex cover is actually an independent set. So again, we're just going to do the same thing. So let S be a vertex cover. Let I be the set of vertices that are not in S. And I claim that, well, I is an independent set. So why is this true? What I need to show is for any pair of vertices, they can't share an edge. So what I want to show is for any U and V that belong in S, sorry, not S, I, U and V do not share an edge. So why is this true? So think about the argument that we made here, where we said, okay, if you had a pair of vertices in S, then not in S, where they share an edge, then they have to be in the independent set. And then this contradicts the assumption that I was an independent set. So how might you write a similar argument for this case? When now we have a vertex cover and we want to show that the complement itself is an independent set. So I guess what happens if I what happens if U and V share an edge? So let U and V be in I. If U and V share an edge, what does that tell me? Right. So I remember that S itself is a vertex cover, so that means um, every edge, at least one of the endpoints need to be an S. And remember that I is the set of vertices not in S. So in fact, what that tells me is, well, if U and V share an edge, so say it shares this edge, um, what that tells me is that there is some edge that isn't covered by my vertex cover. Then the edge UV is not covered by S, right? Because so your vertex cover might look like this, and then maybe I pick these vertices. Um, but notice that if I pick these three vertices, yes, so these three vertices are kind of a vertex cover, but notice it doesn't actually capture this edge. So in fact, the vertices that I pick can't be a vertex cover because there's some edge that isn't hit by the vertex cover, and so that means that this is actually not a vertex cover, right? Because this UV edge can't be covered by the vertex cover. But this is a contradiction because S is a vertex cover by assumption, which is a contradiction. Cool. And so this is true for any pair of vertices in I. So therefore, every pair of vertices in I are not adjacent, which implies that in fact I is an independent set. Are there any questions with this? And so very quickly, the polynomial time reduction. Notice that we didn't really do anything to the graph. So if we want to write a polynomial time reduction from the vertex cover problem to independent set, in fact, we don't. All we need to do is just change the k. So notice that in vertex cover, your input is a graph g and an integer k, and we showed that g has. Well, what we showed is in part A, if you have a vertex cover of size k, if you have an independent set of size k, then you have a vertex cover of size n minus k. So what that tells me is, if I has size k, then S has size n minus k. So in fact, finding an independent set of size k is equivalent to finding a vertex cover of size n minus k. And so all we need to do here is to just write k prime to be equal to n minus k, and then we get a new instance of independent set. So now what we've done is we've transformed our input, which was gk, and we've transformed it into g n minus k. And I claim that the original graph has an independent set. The original graph has a vertex cover of size k if and only if the original graph has an independent set of size n minus k. And these two results here show you that this is actually true. So are there any questions with this reduction? So we need to transform an instance of vertex cover to an instance of independent set and show that in fact the two directions are true. So in other words, if I have a vertex cover of size k in G, then I have an independent set of size n minus k in G. And if I have an independent set of size n minus k in G, then I have a vertex cover of size k. Cool. And then obviously this reduction can be computed in polynomial time because all we do is transform k to be n minus k. Cool. All right, now we'll move on to another question where again all we're doing is just constructing the reduction, and I think just really understanding where the reduction comes from is important, and then we'll go into the complexity classes in the second half. Okay. So here we're given two problems again. These two problems are very similar in nature. So consider the first problem, which is called partition. And in this problem, we're given an array of integers, and our goal is to decide if we can partition A into two sets whose sums are the same. And subset sum just says, well, given an array of integers and a target integer t, can we find a subset of integers that sum to t? And here we want to construct a polynomial time reduction from the partition problem to the subset sum problem. So to construct the reduction, what we need to do is, given any instance of the first problem, construct an instance of the second problem, and then show the equivalence. So let's go through the construction. So our input is an array A of n integers. And what we would like to do is to spit out a new array. So the output is a new array. It could also be the same array, but in general, we just assume that the array is a new array of, say, m integers. And an integer t. And here we get to choose what value of t we want. So any thoughts on what the construction would look like? So let's say it might be easier to think about what happens if the array can be partitioned into two sets, so that they sum to the same thing. So let's say I have an array. A is A1 up to AN. And I know that there's a way of partitioning this into two sets so that they have the same sum. So I can partition this into A1, which is, say, A1, AI1, AI2, up until AIK, and A2 is AIK plus 1 up until AIN. So suppose I know that there is a partition into two sets, and I know that they sum to the same thing. I'll do j equal to 1 to k a I j equals to j equal to k plus 1 to n of a I j. So okay, so suppose I know that these two are the same thing. Do we know the actual sum here then? So if I know that these two sum to the same thing, then in fact do we know this number here? Um, okay, so we don't actually need to assume we know what A1 and A2 are. Just the fact that we know that they sum to the same integer should already tell us what that value is. So we don't even need to know a priori what A1 and A2 are, right? Because the only way for this to happen is what? So okay, so what do we think the integer is, or the number? It doesn't have to be an integer. So what do we think then the number is? So maybe if I look at the entire sum, so I know if I look at the entire sum, so the sum of all of the elements in my array, then what I know is well, because these two sum to the same. So okay, let's try like this. So I know that this is equal to this sum, right? Because uh, this is really a partition of the same sum. To M A I sorry A I J, and then I know that these two things are the sum to the same thing by assumption. So in fact, I know that the entire sum is equal to 2 times the sum of one of my partitions. And so what I know is, in fact, this uh, number here is just half of the entire sum. Right? And there might be some issues with the fact that this might be an odd number, but I think for most of our purposes, we're going to assume that this is even. So that this is an integer. Okay, so what I know is now this number here is a half times the entire sum, right? So what I can do is I can just keep the same b, because if I know that a partition exists, then I know that both of them have to sum to uh, the running sum of the elements of A divided by 2. So in fact, this if I know that this array can be split into two uh, sums of uh, two parts of equal sum, then I know that this t has to equal to a half times the sum. So what I can do is I can do the following construction. So given array A, what I'm going to do is I'm just going to let B be equal to A, and then let T be equal to a half times the sum. And what I claim is, in fact, my original A has a partition if and only if the partition has if only if the partition sums to uh, this integer here. So let's prove the forward direction. So let's suppose that A has a partition. So suppose that A can be partitioned into A1 and A2 such that they sum to the same thing. So if I look at all of the elements in A1, I in A1, they have to be equal to all of the elements in A2. Now, because I know that this is a partition, I know by the previous analysis that we get this. So the sum of all of the elements of A is equal to the sum of the elements in A1 plus the sum of the elements in A2. And then this is equal to 2 times the elements in A1, just by the assumption that they're equal, right? Because you can imagine that this is just the sum of the elements in A1. And so what we can do is, well, in A, there exists a subset, let's call it A1, such that the elements in A1 sum to half times so what we know is that in fact in A we can find a subset A1 such that the sum of all of the elements in A1 actually sum to half times the total sum, right? So here does the forward direction here make sense? So if I know that there's a partition, then in fact there's a subset that sum to exactly half of the total sum. And so that means if I have a yes for partition, then I have a yes for subset sum. And now our goal is to prove the other direction as well. So let's suppose now that there is some subset that sums to t. Suppose that there is some subset subset of b such that okay, so we'll call the subset b1 such that the sum of all of the elements in b1 of b equals to a half times the sum over the entire set. Okay, so this is what we assume because here subset sum is essentially just deciding if we can find a subset of integers that sum to t. Here t is we chose t to be this element here, and b is just a. So now we can just write it as so what we have is the following. So b is just a, so I can just replace b with a. And I know that this sums to a half times the total sum. So what I can do is I can just look at the remaining indices. So all of the elements that are not in B1 actually form the other part of my partition. So then I can go B1 and B2 form a partition of A, and I just need to check that B2 actually sums to the same thing as B1. So then what we have is, well, the elements in B2 of AI, that's just the total sum minus the elements in B1. But remember, this was equal to a half times the total sum. So I get this. And then if I take the total sum minus half times the total sum, this is just half times the total sum as well, which is equal to the sum of all of the elements in B1. Therefore, B1, B2 form a partition that sum to the same integer. And there we go. And now we have our reduction, and we've proven both of the directions for our reduction. Does anyone have any questions with this problem? Is the partition NP complete? It turns out that this problem is NP complete, so this reduction tells us that subset sum is also NP hard, and that you can prove independently that subset sum is also NP complete. Oh, are there any questions with this problem? So why were we able to swap BI with AI? So this was just by our construction. So remember that in our construction, we stated that B was equal to A. So what that means is that for every I, BI was equal to AI. And so instead of talking about B, which is our input to subset sum, we can actually just replace it with A, because in our construction, we only look at the cases where B was equal to A. No worries. Okay, so last one before we take a small break, and then we'll go on to do actual NP hard and NP complete proofs. Now we're going to look at the other direction. So in the kind of the earlier two problems, what we really did was we constructed a kind of NP hard proof, but we didn't really do an NP hard proof because we didn't really state that these two problems were NP hard. We just kind of constructed the reduction and kind of showed that, well, if the first problem was hard, then the second problem is also hard. Now we're going to go the other direction. Now we're going to go from a problem that we want to solve to a problem that we already know how to solve, and show that, well, because we know how to solve the second problem, we can also solve the first problem. So this is kind of the other side of the reduction. So in this problem, we are trying to generalize the idea of a min-cut. So remember that in one of your earlier modules, we said that the minimum cut problem was the problem of determining whether we could find a cut of capacity at most k. And the cut here, remember, completely disconnects S and T. So you might remember this as the min-cut problem. So min-cut is to minimize capacity of cut. Here, we've just turned it into a decision problem just so that it makes our lives a little bit easier. And what we're going to do is we're going to look at a more general, a generalization of this problem, where instead of disconnecting two vertices, what we would like to do is to disconnect a subset of vertices, the two subsets of vertices. So, you are given two subsets. So you're given two subsets S and T, and you're also given an integer k. And we're going to define the subset minimum cut problem to be the problem of determining whether there exists a cut in G of capacity at most k that completely disconnects all vertices in S from all vertices in T. So instead of disconnecting two vertices, we want to disconnect a whole subset of vertices. So now, if we look at, like, say, a subset of vertices and another subset of vertices, what we would like to do is to basically find the smallest capacity cut that disconnects this set from this set. So, for example, if I have something like this, maybe something like this, then one potential cut is just to cut everything here. And this will give you a cut of some capacity. And our goal is to essentially convert this problem into a minimum cut problem. So let's look at part A. So part A says, okay, given an instance of the subset min cut problem, how would you transform it into an instance of the minimum cut problem? So in other words, you want to go from a subset of vertices to two vertices. So how might you do that? Are there any thoughts? So this is S and this is T. So if I look at this diagram and I want to find a min cut for two subsets of vertices, how might I do that? A supersource and a supersink. Okay. So I create a vertex here and a vertex here, and then what do I do? So I have my supersource and supersink. Connect the supersource to all vertices in S. Okay, sure. So I have something like this, and we're also going to do the same with this. Okay? And then I'm just going to orient the edges this way, and I'm going to assume all of the directions are one direction. Okay. Okay. So remember that in the minimum cut problem, we also have weights. So okay, so assuming that we have weights for our black edges, what uh what should I construct here? So what capacity should I place for each of the new edges that I've created? Infinity. Yep. Why is it infinity? Exactly. So we essentially want to uh so we want these edges to be of infinite capacity because we want to ensure that all of the vertices all of the edges that are actually cut by the minimum cut are edges that actually belong in the original graph. So if I were to do it if I were to make it some finite value, then this wouldn't work because some of the edges here might be cut in when we solve the minimum cut problem. But the infinite capacity ensures that we never cut these edges. Okay, so this is our transformation. Now we've converted into an ST problem where now we can just run uh, our max flow our max flow algorithms. So here we've just done part A. So what we've done is we've constructed a super source, super sink with infinite capacities on all of the edges we create. Then we solve the corresponding min cut problem. Uh, so okay, so suppose I solve the min cut problem. How does that solve the original subset min cut problem? So imagine we ran, our Ford Fulkerson algorithm or Edmonds car algorithm, and it gave us a solution. Um, how would you use that to solve the subset min cut problem? Or like, what does that tell you about the original min cut problem? I did V. So remember, there was a reason why we had infinite capacity edges. So infinite capacity edges uh, means that any edge that is included in my min cut cannot come from any of the new edges in the min cut. So what that tells you is, in fact, all of the edges that belong in the min cut have to disconnect the vertices from S, the vertices in S from vertices of T. So edges in min cut come from original. So yeah, so edges in the min cut come from original graph, and then the last thing is to realize that, well, um, when we construct our min cut, it has to separate S from T, so therefore it must separate S and T. And so the same min cut can be used to solve the original problem here. Okay. And hence explain why the subset min cut problem can be solved in polynomial time. Well, you can solve the min cut problem in polynomial time, and then using the same algorithm, you can solve the subset min cut problem. So hopefully this is quite straightforward. Um, it comes directly from the fact that we can solve minimum cut in polynomial time. Are there any questions with this problem here? So hopefully this was kind of another uh, way of looking at reductions. Reductions aren't just used for looking at hard problems, but also we can transform our problem into a problem we've already solved, and then use that algorithm to get what we want. Cool. We will take a small break, and we will come back where we actually start talking about uh, some of the complexity classes. Okay, could you explain how it runs in polynomial time with respect to the input? Sure. So here, remember the transformation that we did is, so here the transformation is polynomial time. All we do is we construct all of these edges and all of these weights. So the transformation itself is done in polynomial time. So I guess we'll step through the algorithm a little bit. So the algorithm itself is transform input to min cut. And the transformation is to add edges. And the number of edges we add is at most the number of vertices. So number of edges is O of n. And though we add weights, so each weight can be added in constant time. So in fact, the number of weights that we add is O of n. So it's O of 1 for each new new edge. And then the last thing is to just add two vertices, and that can be done in constant time. That's all of 1. So the construction from the input to the min cut problem can be done in linear time. Then the second thing to do is to solve min cut on input, and the input itself is a transformed input, and this is done in polynomial time. So remember that if you use Edmonds COP, you get v times e squared. And here, the number of vertices is, well, the number of vertices plus 2. So that's still going to be O of n. Number of edges. Well, number of edges is bounded by number of edges time number of edges plus the number of vertices. So this is going to be bounded by m plus n squared. And then the third thing is to just read input or read output, right? And this is done in constant time because the output itself is going to give you, a number. It's going to give you the capacity of your cut, and that same capacity is used for the original problem. So in all, if you look at the algorithm, it's transforming inputs to min cut, which takes O of n time. Then you solve the min cut problem on the input, which takes time in the order of n times n plus n all squared, and then you just read output, which takes constant time. So the entire algorithm would take something like O of n times n plus n squared, which is polynomial in the input. Does that make sense? So here it would be polynomial in the length of the graph, or I guess flow network in this case. Are there any questions with this? Would this be a reduction if poly time in poly time? So the reduction is polynomial time, right? Because um, you're given the graph as input, and then the actual transformation only takes linear time. So you just add a bunch of edges, you add a bunch of weights, you add two vertices. That all of that takes at most the number of vertices. So the actual transformation, the reduction itself is itself polynomial time. So this is the reduction, and the reduction takes linear time. What is the length of the graph? So here we are given essentially just a graph representation. So anytime you want to represent a graph, or anytime you want to encode the graph, you encode it by the vertices and the edges. So you encode it by the the vertices and then the relationships between any pair of vertices. So what you can do is there are two main representations. So if you use a graph adjacency list, then what you do is for each of my vertices, I create a linked list of all of my neighbors. And so to represent the graph using an adjacency list, I only need to store the number of vertices and the length of uh, the neighbors. So this would be at most O of V plus E. And in fact, for any arbitrary graph, the actual representation is bounded by O of V plus E. If you want to use a graph adjacency matrix, then this would be O of V squared, because you create your V1 up to Vn, V1 up to Vn, and then you basically fill in this matrix. So in general, the length of my graph is always V plus E, which is N plus M. So you want your algorithm to be polynomial in terms of N plus M. And here we can see that this is polynomial in terms of n plus n. Does that make sense? Now, in terms of weights on graphs, generally you can assume you have access to some kind of oracle that gives you the weight of the. Um, so let's just mention that weighted graphs have length e log w. So this assumes that. Okay, so there's a couple of ways to represent the graph with weights. So generally, what you can assume is for a weight, you have access to some kind of oracle function that, given two vertices or given an edge, it gives you the actual weight. So generally, whenever we talk about weighted graphs, okay, maybe I'll do this. Um, you're actually given the following. So you're given the graph structure. So the input is a graph G and a weight function W from the pair of vertices to some real number. And generally, okay, so we don't have to assume anything on the weights. Now, there are different ways of representing the graph. The most succinct way is to say, okay, you're given the graph structure, so you're given the unweighted graph, and then you're given a weight function as a black box oracle. So you can assume that the weight function is given as an oracle, which means that, okay, so if it's given as an oracle, then it takes O of 1 to return the weight of a um, of an edge. So in other words, you can kind of store the weights in an array of edges. So you can imagine that you have an array of edges, and you essentially just so imagine you have this array E1, E2 up until E the size of E, and in each of my uh, in this array, you're basically given the weight. So this would be the weight of E1, the weight of E2, and so on and so forth. And here, if you assume this kind of structure, then the representation here is really just dependent uh, on the graph. Uh, because like we don't really care about what the weight is, so we don't really care about like the maximum weight, because that's actually not really that important to us whenever we construct these kinds of um, algorithms. So generally, we can assume that the wave function is given as a black box oracle. We don't have to care about the representation of this function. If you care about the actual representation of this function, then you essentially have this array, and you this array has size uh, e times log of w, where log of w is the weight is the bit representation, or I guess bit length of the largest weight. Um, here, like, it's a little bit annoying because now that we have like infinite weighted edges, there is no real succinct way of representing that, which is why we generally don't care about the weight itself. And so whenever we talk about weights, we just treat it as you have access to this function, and we don't really care about how the function is actually represented. And this is the general consensus for most things whenever we're dealing with weighted graphs, because the weights themselves aren't really too important, or like the way that we represent the weights really aren't that important. Um, and so this is the general setting that most people will deal with. Does does this make sense? And so yeah, like representing infinite weighted edges doesn't really incur much cost. Awesome. Um, if you have any questions with this, uh, feel free to post it on the forum, and I will also try to explain exactly what it all means, because different people have different opinions also on how things should be represented. Generally, as you know, so someone who works in complexity theory, we generally don't really care about representing weights of edges of graphs. This is something that most people just don't really care too much about. Cool. Alrighty. Now we will cover. Okay, so now we will actually cover some of the NP completeness proofs. So let me just erase this so I have space. Okay. So now we're going to cover some proofs where we actually do NP complete proofs. So the first problem is something called almost Hamiltonian path. So as a reminder, this is what the Hamiltonian path problem is. So given a graph, does there exist a simple path in G that visits every vertex exactly once? And almost Hamiltonian path is essentially a Hamiltonian path, but you miss 2025 vertices. So is there a path in G that visits every vertex but 2025 of them? And what you want to do is you want to show firstly that this problem is in NP, and this should say 2025. I'll get that changed. Okay. So to show that this is in NP, let's suppose I have a graph. So, sorry, a path. So let P be the path. And all I'm going to do is just to check that this path is a Hamiltonian path. So there is really one thing we need to check, or two things we want to check. So the first thing we want to check is the size of P equals to n, right? So the number of vertices. I guess we'll do this. So number of vertices in P equals to n. And two, well, this is a simple path. So every vertex is hit or is visited exactly once. Okay. So for the first part, this is fairly easy, right? Because if we're given the path, let's say the path is given by P1, P2, up until Pn, where Pi is the ith vertex that is visited in this path. All we need to do is to check that, well, indeed, there are n vertices. So this can be done in O of n time, right? Because all you need to do is go through the path and just keep a counter of the number of vertices in the path. So this is easy to check. Second thing is to check that, well, this is a path. So we need to check that pi to pi plus 1 has an edge in G. Again, this can be done in polynomial time. Well, actually, this can be done in constant time for each consecutive pair of vertices. And really, the third thing to check is to check that every vertex is visited exactly once. And I will leave it to you to basically check that all three of these can be done in polynomial. So to check that, it's a path that visits every vertex exactly once in my graph, except for 2025 of them, actually. Actually, what we need is... Oh, sorry. I did the wrong problem. So actually, what we need to do is we need to check the following. P of n minus 2025. So what we need to do is check that 2025 vertices are missed. So every vertex but 2025. And I'll leave it to you to check that this is easy if you're given the path. So, for example, if I'm given my path and this is my graph, maybe it looks something like this. And then I have, a bunch more vertices. Checking that it's a path is easy, right? Because you just check that every pair of consecutive vertices share an edge, and then you just have to check that 2025 of them are not in the path. So all of this can be done in polynomial time. So the problem is in NP. Okay, so that's the easy part. The hard part now is to show the reduction. So now we're going to show that it's NP hard by essentially reducing from the Hamiltonian path. So let's say I have a graph. So let G be a graph. And what I'm going to do is, if I know that G has a Hamiltonian path, then I want to make sure that the graph I generate has a path that visits everything but 2025 vertices. So how might I do this? Well, let's suppose I have a Hamiltonian path. So let's suppose that my Hamiltonian path looks like this. What I want to do is I want to make sure that in this Hamiltonian path, I construct a bunch of vertices so that I miss 2025 of them. And the easiest way to do this is to just generate a bunch of vertices that my Hamiltonian path would miss. So let's suppose I generate 2025 isolated vertices. Then for sure, in this new graph, I have a path that visits every vertex except for 2025 of them. And the goal is to now prove the other direction. So let's actually write it out in full. So construct a new graph G prime given by V prime and E. So here I'm just going to keep the edge set the same, but I'm going to create a new vertex set where V prime is just V union a bunch of new vertices, V1 up to V2025. And I claim that G has a Hamiltonian path if and only if G prime has a path that misses 2025 vertices. Okay. So for the forward direction, suppose G has a Hamiltonian path Okay, so G has a Hamiltonian path. That means if I look at the construction of G prime, all I've done is I've just added some isolated vertices. In fact, I've constructed 2025 new vertices. So this path must pass through every vertex in V, but this misses the vertices V1 up until V2025. So therefore, G prime has a path that misses 2025 vertices. Cool. So that is the forward direction, where if your graph has a Hamiltonian path, then the same path that you use must actually miss all 2025 new vertices. Now, let's suppose the backward direction is true. So suppose G prime has a path that misses 2025 vertices, right? Well, if G prime misses 2025 vertices, then what I know is, in fact, the 2025 vertices that it must miss are exactly the vertices we create. So since there is no edge between Vi and Vj for all I and j in the set 1 to 2025, G prime has a path that visits every vertex in V exactly once. But remember that the this graph here, the ones that don't include my 2025 vertices that I've created, well, that graph itself is the original graph that I've created. But this is just the graph G, which implies that in fact G has a Hamiltonian path. Does this argument here make sense to everyone? So what I've shown is in the forward direction, if I know that the original graph has a Hamiltonian path, then the new graph that I've created must have a simple path that visits everything but the 2025 vertices that I've created. And so that means that my new graph has a path that misses the 2025 vertices. And in the backward direction, let's suppose you have a path. You don't know originally that the path itself must belong in the original graph, but let's suppose that the path itself misses 2025 vertices, and we can assume this by assumption. Well, the claim is, since you know that no pair of vertices, no pair of new vertices that I've created have edges between them, these are exactly the vertices that must be missed, because there is no path that includes any of the vertices that I've created, which means that the path that it must have created has to belong in the original graph G. And therefore this G is this G would then have a Hamiltonian path. And so therefore we've shown both of the directions. Are there any questions with this proof? any part that maybe doesn't really make sense. If not, then we can move on to the second last problem. So here we're gonna do a few more proofs. So hence conclude that almost Hamiltonian path is NP complete. So here, um, we're also going to check that this construction is done in polynomial time, but this is easy because if you look at the construction, all we've done is added 2025 new vertices, and this is clearly done in polynomial time. So the reduction can be computed in polynomial time. And so since Hamiltonian path is NP hard, it's actually NP complete, but NP hard is usually good enough. This also implies that almost Hamiltonian path is also NP hard. And that implies that um, uh, almost Hamiltonian path is NP complete. Right? Because we've shown that almost Hamiltonian path is NP by part A, and then in part B, we've shown that almost Hamiltonian path is NP hard. So we conclude that it's NP. Okay. Now we'll go to another problem. Here we are given a pair of problems. So the first problem is again the independent set problem. Given a graph G and given an integer k, can we find a subset of at least k vertices that form an independent set? And then the new problem is given a graph and an integer, does there exist a subset of at least k vertices such that firstly S has to form an independent set, and every vertex in my independent set has to have degree at least k in G. So the first part is to show that high degree independent set is in NP, and then we're going to show that it's also NP hard. So I'll leave it to you to check that high degree independent set is an NP. All you need to do is, given your set, you just need to check that it's an independent set. So check independent set property. So you just need to check for every pair of vertices in S, just check that they don't share an edge. You can do this in V squared time. And then the second thing is to just check that every vertex in S has to have degree at least k. So check that every vertex has degree at least k. And it's very easy to see that this can be done in polynomial time. So it can be done in poly time. Cool. So, okay, so we've just shown that it's an NP. Now we need to show that it's NP hard. So what we're going to do is we're going to reduce from the independent set problem, and we know independent set is NP complete. So let's write that. So we reduce from the independent set problem Okay. So the independent set problem has two inputs. So it has a graph and an integer k. And what we would like to do is to construct a new graph and potentially a new k, so that if the original graph has an independent set of size at least k, then in fact the new graph needs to have an independent set of size at least k or k prime, where every vertex has degree at least k prime. So, any thoughts on how we could do this? So let's suppose I have an independent set. Now the issue is some of these. Okay, let's suppose I have something like this, and I know that k is 4. So this is clearly an independent set of size at least 4. So if I just choose these vertices, but the issue is not every vertex has degree at least 4. So how might we construct maybe a new graph where we are guaranteed that um, if we had an independent set, then the independent set itself would have at least where every vertex of that independent set has degree at least k, or some other function of k. So you can kind of see the problem here right now is um, that we aren't really guaranteed the degree of the vertices in my independent set. So what we would like to do is to basically guarantee that every vertex, like if we were to pick that vertex in my independent set, then uh, that independent set, all of the vertices in that independent set must have at least degree at least. So to do this, all we're going to do is to just blow up the degree of each of my vertices, so that no matter what independent set I pick, each of my independent set must have degree at least k. So here, what we would like is, so the hint is to blow up the degree of each vertex. So if I were to construct an independent set, then no matter what independent set I choose, then all of these independent sets must have degree at least k. So for each vertex, let's call it v. Okay, we'll call it vi. We're going to construct vertices. Let's call it ui 1, ui 2, up until uik, and connect each uij to vi. Right. In other words, if I have a particular vertex, no matter what degree it's already, so even if it has degree at least k already, what we're going to do is we're still going to blow it up anyways, because there's no harm in just blowing up all of the vertices. So what I'm going to do is I'm actually just going to create a bunch of vertices that aren't connected to anything else except for this particular vertex. And what I know is that this vertex now has to have degree at least k, because it has to at least be connected to all of these k vertices that I've created. it might have degree strictly greater than k if it's already connected to some other vertex. So for example, if I have something like this, but at least I know that this vertex that I choose must have degree at least k to begin with. Okay. And then I claim that if the original graph has an independent set of size at least k, then the new graph that I've created, just by doing the blow up, has to have an independent set of size at least k, and the other property that every vertex has to have degree at least k. So let's prove this equivalence. So what I'm going to do is, well, let's suppose that G has an independent set I, and I'm also given that I is at least k. Well, in G prime, any of my independent sets must have degree at least k, right? Each vertex has degree at least k. And the independent set of G is still going to be an independent set in G prime. And I is still an independent set in G prime. And we're done. So we've blown up we've blown up the degree of every vertex. So first of all, if it's an independent set, it's still going to be an independent set. And the second thing is, if it has degree at least k, well, like every vertex has degree at least k in G prime. So no matter what vertex I pick in G, that must have degree at least k in G prime. So we're done. Okay, now we're going to prove the backward direction. So suppose I have a high degree independent set. But suppose that G prime has a high degree independent set. I prime. Now, it's not as obvious as the forward direction why this would imply that the original graph has an independent set. Because maybe it could be that some of the vertices that I pick don't come from G. So if you imagine the original graph might look something like this, but then I blow up every vertex. And what I claim is, well, even if I blow up all the vertices, the high degree independent set must come from the red vertices here. Because if I had something like this vertex, and this vertex, why is this not a valid high degree independent set? So in other words, why does my high degree independent set need to come from the red vertices? And here we're going to assume k is at least 1. If k is 1, it's trivial, so k is at least 2. So why is it the case that I cannot pick a green vertex? Exactly. The green vertex has degree exactly 1. And here we're making the assumption that k is at least 2, because k go to 1 is trivial. So we can't pick any of the green vertices because, well, the green vertex only has degree 1. So any vertex in V of G prime, but not in G, has degree 1, which is smaller than k. So therefore, I prime is comes from G, and we're basically done, right? So you can't pick this vertex, so therefore it must be this vertex that we ended up picking. And so because G prime has a high degree independent set, and the vertices that we use from G prime actually come from G, that implies that G itself has an independent set. So, oops. So this implies that, in fact, G has a independent set of size at least k. And we are done. Cool. Are there any questions with this reduction here? I'll scroll. If there are no questions, then we just double check that everything can be done in polynomial time. Well, for each vertex, you just blow up, you create k vertices. And here we're going to assume k is a polynomial in the size of g, or in the size of the graph, because otherwise it's not really that meaningful. So here, the representation is, so reduction can be done in polynomial time. And then, so yeah, we've proven both of the directions. And then the last thing to do is to basically conclude that it's NP complete. So here we have that independent set is NP hard, which implies that high degree independent set is NP hard. And then because it's both an NP and NP hard, we conclude that high degree independent set is NP complete. Cool. And then we have one more question, which is about balloons. So let's do one more reduction, and then we'll call it a night. So a balloon subgraph is a undirected graph that consists of a simple cycle of length k and a simple path of size k, where the path contains an endpoint that lies on the circle, on the cycle. Every other vertex on the cycle is disjoint from every other vertex on the path. So in other words, it's just going to be a cycle followed by a path. So a path is going to be connected to some vertex on the cycle, and it is of size k if the path. So if the path has length k plus 1, including the vertex that is connected to in the cycle, and the cycle itself has size k. And so our goal is to show that it is NP complete to decide if G has a balloon subgraph of size at least k. So again, we're going to prove two things. We're going to prove membership in NP. To prove membership in NP, what we would like to do is, well, we just need to verify that the subgraph that I'm given is a balloon. To check that cycle has at least k vertices, And then I'm going to check that at most, or exactly one, vertex on the path is connected to cycle, and then check length of path. So each of these can be done in polynomial time. Checking that the cycle has at least k vertices, you basically just count the number of you basically count the number of vertices in your cycle. Then you check that the path has length k plus 1, and then you check one vertex is connected to the cycle. So this obviously can be done in polynomial time. So the problem is in NP. To show that the problem is NP hard, we need to reduce it from a well-known NP hard problem. So here we know that the balloon has a cycle followed by a path. So yeah, the question is, what happens if this is a Hamiltonian path, Hamiltonian cycle? And this is kind of the key part, the key point. So if we know that this itself is a Hamiltonian cycle, then the path itself needs to have length n plus 1. So the path has length n plus 1. In other words, we choose the k to be n. So here's the actual formulation. So we reduce from Hamiltonian cycle. So given a graph, G, what we're going to do is we're going to construct a new graph, call it G prime, where V prime is just V with n with n vertices. So we're going to get V1 up to Vn, and E prime is just going to be we connect V1 Vi to Vi plus 1 for each I, and then we're also going to connect V1 to some arbitrary vertex. So connect some arbitrary vertex x to V1 as well. So in other words, the construction of the graph kind of looks like this. Suppose I have a graph that kind of looks, I don't know, something like that. What I'm going to do is I'm just going to add k or n vertices. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. And I'm just going to attach the first vertex to some arbitrary vertex that I choose. And so you can see here, if I have a Hamiltonian cycle, let's say I have something like this, actually. So let's suppose I have a Hamiltonian cycle. Does this have a Hamiltonian cycle? Yes, it does. So if I had something like that, so this will be my Hamiltonian cycle. Oh wait, it's not a cycle. Let's suppose I ignore this. So very clearly, it will have a Hamiltonian cycle. So I construct the Hamiltonian cycle here. which is basically just this cycle. Well, if I just add on this new path, then this is my balloon, right? And so, and likewise, if I don't have a Hamiltonian path, something like this, then I claim that we can't have a balloon here, because the balloon here can't consist of this vertex. So let's actually prove this formally. So what I want to do is I want to show that if G has a Hamiltonian cycle, so suppose that G has a Hamiltonian cycle, then what I know is the balloon is just really going to be the cycle plus this path. So we can construct this the balloon by appending the path to the cycle in G prime. And this balloon has size n, right? Because the cycle itself has length n, and then the path itself has length n plus 1. Okay. In the backward direction, suppose that G prime has a balloon of size n. Okay, well, what does it mean? Well, we can decompose the balloon into a cycle and a path. So let the balloon be equal to the cycle plus the path. So we'll call it C plus P. Well, what you know is the path okay, we'll say, okay, the cycle cannot contain any vertex that we construct, right? Because if it did contain a vertex that we constructed, say, let's say here, well, what we would need is something like some vertex connected to this vertex, and then some other vertex connected to this vertex. But the fact that we only connect this vertex to one vertex means that we can't actually form a cycle using any of the vertices that we constructed. Therefore, the path is the set of vertices that we constructed, and the cycle can only come from G. In other words, the cycle itself can only come from G, but remember that the balloon has size n. Balloon has size n. Implies that the cycle has size n. But this would imply that, in fact, the cycle is a Hamiltonian cycle, because the cycle would contain every vertex in the original graph. The cycle is a Hamiltonian cycle in G. And so, therefore, because Hamiltonian path is NP hard, this would imply that balloons is also NP hard. Uh, and this implies that balloons is NP complete. Right. And you just double check that the reduction is polytime. Cool. So this is the general scaffold whenever it comes to writing a reduction. You want to actually start with some problem that is known to be NP hard, and then construct an instance of your problem from an arbitrary instance of the original problem, and then show that if the original problem has the property of the NP-hard problem, then the graph that you construct, or the instance you constructed, must satisfy the property of your problem. And then if the instance that you constructed has the property that you need to satisfy in your problem, then the original problem, so the original problem, um, the original instance satisfies the property of the original problem. So this is kind of the general scaffold, and then you just verify that the reduction takes polynomial time, and then therefore the problem is NP hard, and then you show that it's also NP, which implies NP completeness. Okay. Does anyone have? Do we need to memorize the problem examples in NP hard? So in the exam, you will be given the problem itself, or you'll be given a list of problems. So either you'll be given a problem, or you'll be given a list of problems. So you don't have to memorize all of the NP hard uh, problems. Um, in your lab, there is one question that asks you to just show that it's NP hard without actually giving you the problem to reduce from. In that case, you do need to think about like what kinds of properties the problem has and how, and then like what problem you want to reduce from. So hopefully, just by thinking about the problems a bit more, maybe visually or geometrically, you can kind of see certain parts of the problem that look very similar to uh, other problems that you might have seen. So, for example, with the balloon, right? We had a cycle. So every time you have a cycle, maybe the thing to think about is to go from Hamiltonian cycle to your problem, or maybe this one was an independent set, so maybe you want to go from an independent set to this variation of the independent set problem, or if you have some kind of path problem, so does there exist a simple path? Then maybe you want to look into Hamiltonian path or longest path, something like that. Cool. Are there any other questions? If there are no questions, then we'll probably end it here. So next week we will finish off with some more reductions and maybe some linear programming as well. So hopefully that will be quite fun, and that would also be helpful for anyone doing the HD problem as well, where you're asked to come up with you're asked to show that the rounding is a two approximation. So I think next week we will try to cover a two or three approximation for another problem. Cool. If there are no questions, then we'll probably end it here.